Hello, welcome back to three-phase circuit analysis. We're doing Y delta problems. This is problem 5 in the Y delta case, source load Y delta. And finally here we get the payoff. We've spent a tremendous amount of time, long time ago, doing YY circuits, learning how to do single-phase equivalent, learning how to solve YY circuits. Then we introduced a delta load, and we spent a lot of time deriving things and how to work with delta loads. And then we spent the last few problems doing what I call baby problems. Just a little shifting here and there to teach you how to deal with a delta load. This is our first real problem, and you can see just by looking at the complexity of it, the reason why I broke it all up into chunks. But now, if you followed me step by step through this process, then this entire problem, which looks gargantuan, is actually going to be quite simple, because by now you should start be thinking logically about how to approach it. But there are a lot of steps here, there are a lot of gotchas, and there's actually at least one case in here where I'm going to show you 2 different ways to attack it and show you, by actually working it, that you get the same answer both ways. So there is a lot of meat on the bones in this problem. So let's get started. And buckle in, it's going to take us a little while to get through it. All right, so we have a Y-connected generator. It has an internal phase voltage of 120 volts per phase, and it has an internal impedance of this, 0.2 plus J0.5. Okay, that's the generator side, and it says it's a Y source, right? Then it says it feeds a delta load, and the delta load has this in terms of its impedance for the delta configuration, 118.5 plus J 85.8 ohms per phase. Then it says the line impedance is 0.3 plus J 0.9 ohms per phase. And it's telling us to use the A phase of the generator as the reference. And this last part is kind of cryptic, but it's telling me a positive phase sequence. I didn't write it all out because I'm trying to keep the board nice, because we're going to be having a hard time fitting all the math on this anyway. So I didn't want to put another line. But anyway, basically we're using the A phase of the generator as a reference, and we're having a positive phase sequence circuit. Now we have a bunch of things to talk about how we're going to find them, and we're going to do those step by step. But before we do that, let's go through this one more time and just kind of outline. First of all, this is a Y delta configuration because it tells you it's a Y generator and a delta load. Then it tells us everything there is to know about the generator. It tells us the phase voltage of the source, and it tells us the internal impedance of the source, and it's in a Y configuration. And then it tells us it feeds the delta load, and we know everything we need to know about the delta load, because all we really care about is the impedance, and we know it's balanced, so each of the 3 phases of the triangle is going to have the same impedance on the load side. Then it talks about the line impedance, and it gives us the line impedance, which again is the same for all 3 lines. So that's another piece of information we need. And then the last thing we already talked about. So it tells us we know everything we need to know about the source, everything we need to know about the load, everything we need to know about the line. So we have enough information to draw the complete 3-phase circuit in all of its glory. All right, now what did we ask to find? First step, draw a single-phase equivalent circuit. Now this is our first step here, but in reality, it doesn't matter what you have on an exam or in a quiz. If it doesn't ask you to draw that single-phase equivalent, you must draw it. It's like a physics problem. When you have inclined plane or pendulum or gravity or whatever, you always draw something. You have to in order to write the equations properly. If they don't ask you to draw a single-phase equivalent, please just draw it anyway, because if you don't, you're going to get something wrong for no reason. Step 2, find the line currents. Okay, now after this, I'm not going to talk in detail about this, but step 1 and 2 are basically peanut butter and jelly. We want to draw the single-phase equivalent circuit for the purpose of finding these line currents. So it's the next logical thing to find, even if you weren't asked to find it in this problem. So in future problems, for instance, maybe I give you all this stuff and I don't even ask you for A and B. I don't ask you. I say part A, do this, part B, do this, and part C, do this. Don't try to jump right into doing this phase voltage stuff initially, because you're going to need to draw a single-phase equivalent for every problem, and you're almost certainly going to need to calculate these line currents, because it's our gateway into figuring out what the load is doing. So I guess I'm trying to say, I'm babying you a little bit, telling you to find these 2 initially, but even if I didn't, you have to find them anyway. So kind of start thinking for yourself a little bit when your problem doesn't ask you that, to do it anyway. Next, we want to find the phase voltages at the load. Phase voltage at the load means, translating words into math, we want to find the voltage across this phase of the load, and then of course the other ones as well. So we want to find the phase voltage is exactly the same thing as the line-to-line voltage for a delta load. That's what we're trying to find. And then it's asking us to find the phase currents at the load. phase current means IAB, the current through this phase, BC, and CA. So we want to find these three different currents. That's what this is asking us to do here. And then the last thing is find the line voltages at the source. And that is basically going to be, this is a line-to-line voltage at the load, but on the other side of the line, we have the source. We want to find V little a, little b, which is going to be the line-to-line voltage over at the generator end. That'll become a little clearer on what we're trying to find when we draw our circuit, when we write our single-phase equivalent circuit. Okay, so I told you to buckle in. We have a little bit of work to do in front of us. The first step is to draw a single-phase equivalent circuit. All right, what I'm going to do is draw the single-phase equivalent here to keep that board free to write our math. Now, every single-phase equivalent is going to have a generator of some kind. Right? So let's go ahead and draw it there. And then we got to look in the problem statement and see what else is it asking us. It's a Y-connected generator, internal phase voltage of 120 volts per phase. So the way you write this is 120, and it's telling us that's voltage, that's true, but what's the phase of this guy? It's a phasor, but it tells us here in the last sentence, use the A phase of the generator as the reference. When it tells you to do something and treat it as a reference, that's what you need to do. You basically know that that's telling you that this is 120 volts at a 0 degree phase angle, and that is the magnitude and phase of the source. All right, so let's keep going up. We know we're going to have a source impedance here. It has an internal phase voltage of this. Impedance, that's the impedance of the windings in the source, in the generator, 0.2 plus J 0.5. So it's resistive plus inductive. You can tell that by the signs of everything. And it's 0.2 plus J 0.5. So this is 0.2 ohms, and this is J 0.5 ohms. Okay, so we know what the inductance is here, and we are smart enough to know that these are ohms. So just to kind of clarify the drawing, I'm just going to kind of leave it off there. So it's 0.2 plus J 0.5. This is 120 volt with a 0 degree phase angle. All right, it feeds a load, that's true, but let's skip over that for a second. It also goes into a line impedance, which is given by this. So that's the next thing we have to do. It's a resistive component with an inductive component. You can see that because these are both positive here. And what are the values? 0.3 ohms and then 0.9 ohms. All right. Now here you can take a little break here and remember that between your source, which is all this stuff, and your line, we denote lowercase a. And then where we connect the line to the load, we denote that uppercase a. So we want to keep that convention going through all of these circuits. Now here's where it starts to get a little bit crazy. Not crazy, just this is where you have to start to think a little bit. If it were a YY circuit, then the impedance of the load, which would be the Y, configured, the actual Y impedance of each leg of that Y, that would be, if it were a Y load, that would just be right here. But this is not a Y load, it's a delta load. So this impedance here is not the one that you put in your single phase equivalent circuit, because if you think about it, coming back through the line here, this is the line, what impedance do you put? This one, or some parallel combination, or what about this one down here? It's a little different. When it's a Y load, it's very easy to see how the single phase equivalent is constructed because it's just one load coming down, then it splits off. But as we've done a problem before, what we do is we convert this delta impedance into an equivalent Y impedance. So what we say is Zy is equal to Z delta divided by 3. We can do this only because it's a balanced load. In other words, these values are the same, this is a balanced circuit, so we can do that. So what we do is we say Z delta, what is Z delta? It feeds a delta load of, this is what it is, 118.5, J 85.8. So we say 118.5 plus J 85.8 divided by 3. So what this tells us is the equivalent modeled load, if it were not a delta, we could equivalently model it by a Y load, which each leg of the Y would have an impedance of 39.5 plus J 28.6. And this is ohms per phase, of course. So what this means is that the real circuit we've built is actually a delta with those values that are given in the problem statement. But if we actually cut the wires here and throw this delta in the trash can and then build a Y load where it comes down and splits off as a Y and connect those three terminals to the line, but but have each leg of the Y, this impedance here, then equivalently from a generator and a line point of view looking at the load, they would behave exactly the same way. So we can take one load out and we can stick another load in, even though that's not actually what we have in our problem. It's useful because now we have an equivalent Y load of this guy for each of the leg of the impedance there. And why do we need to do that? Because since this is an equivalent Y, we can use this in our single phase equivalent circuit, like this. We can't put the delta load there because it's all in parallel and stuff. So it doesn't even look like a single loop because obviously whenever it gets over here to the load, it starts splitting. But if we replace it with this, it would look like a Y coming back around to the neutral. So it's 39.5, J 28.6. So it's 39.5 ohms, J 28.6 ohms. Now we're almost done with the single phase equivalent circuit. We have two other things to write. Not super important. But on the source side, at the other side of this terminal, we always put a lowercase n. That's the neutral. That's where all the other phases that we haven't drawn here are connecting here to the other side of this power supply generator. And then on the load side, we put a capital N for the neutral connection here. Now here's where students start, and me too when I first learned this, where you start to go off the rails. You start asking yourself, why are we putting a neutral terminal here? In our real circuit with a real triangle, there is no neutral terminal, so why am I putting a neutral terminal there? The answer to the question is, you're right, there is no real neutral terminal in the real circuit you've drawn. But for the purpose of the first part of the analysis, the first part where we're trying to find the line currents anyway, we're going to cut this load out, throw it away, and replace it with an equivalent Y load. Even though we haven't built it like that, we're doing it to help us find the line currents. And even though it's not real, for the purpose of the single phase equivalent circuit, for the purpose of finding the line current, which I haven't drawn here, IAA, that's what we want to find for the first part of the problem. For the purpose of finding this load here modeled as a Y connected load does have a neutral terminal. And if we were to build it and connect that back to the neutral of the source, this would be an equivalent single phase equivalent circuit. So you're right, there is no real neutral terminal there, but it's still useful to kind of pretend that it's there because we're modeling it by a Y-connected load, which would, if we were to build it, have a neutral terminal there. So the reason I'm harping on it is because I'm going to use this terminal here for a calculation later on, even though it's not even really in the circuit, in the real circuit. We're going to actually use this. So I do want you to put little n and big N in your single phase equivalents here. Okay, so first thing we did, we take the load, divide by 3, we get an equivalent Y load, we stick it in our single phase equivalent. Part A is now complete. This would give you full credit on an exam. You have the source voltage, the source impedance, the line impedance, just checking myself here, and the load impedance. Part 2, find the line currents. All right, this is why we draw a single phase equivalent. This is why we take the delta load and model it as a Y so that we can put it here like this, because now it's very easy to find IAA. IAA is going to be the voltage, the only voltage you have in this circuit. It's all just one loop, so it's divided by the sum of all these impedances. Now you're right, this impedance doesn't actually exist in the circuit, but from an equivalence point of view, it behaves from a line current point of view looking that way as if it were there because this load impedance can be completely replaced by that equivalent Y configuration. So even though it's not there, it's equivalent just to help us find IAA. That's why we're doing it. So this current is going to equal this voltage divided by the sum of all this stuff is the bottom line, and that is what we're going to do next. And I'll try to be concise about it here. So we have I little a big A is equal to 120 and an angle of 0. That's the voltage of the source. We have a big fraction. And then here we have 0.2 plus J, 0.5, plus 0.3 plus J, 0.9, plus 39.5 plus J, 28.6. Look, I just barely made it. Okay. Stick this in your calculator, stick all these complex numbers, add them all up, you'll get a single complex number, divide them. What you will get is I little a big A is equal to 2.4 at an angle of negative 36.87 degrees amps. I can circle this one because this is the A phase, right? So this is the line current. So this is the actual load connected to a line, connected to a source. This is the line current flowing between the source and the load. Okay, and it's negative 36.87 relative to what? Relative to my source voltage over here for the A phase. It means it shifted in time to the left, the cosine shifted to the left. Okay, now it asks us, find the line current IAA, but also BB and CC. How do you find, it's a three-phase set, so you have to add, subtract 120, and you remember it's a positive phase sequence. So when you have a positive phase sequence, I always recommend, as I've always said, draw a little diagram. If this were the A phase, ABC is a positive phase sequence. So that would be, this would be a B phase, this would be a C phase. A, B, C, positive phase sequence. To go from here to here, you subtract 120 to go from A to B. And from go to A to C, you add 120. So all we have to do to calculate the B and the C line currents is do that addition and subtraction. 2.4 angle negative 3687. So to go to the B phase, we subtract 120 degrees, like this. And so then I, B, B, I'll try to fit all this stuff, 2.4 at an angle, let's see, what does it come out to? Negative 3687 minus 120, so it comes out to negative 15687 degrees, amps. Of course, it's RMS, as usual. That's the B phase. C phase is the same magnitude, 2.4, angle, negative 3687. That's the A phase. Then you add 120 to that. And so you get ICC, 2.4 angle. When you add these guys together, you get 83.13 degrees amps. Okay, so you have the A phase, which comes from Ohm's law, from the single phase equivalent circuit. To find B, you subtract 120. To find C, you add 120. Of course, if the phase sequence were negative, it would affect which one was added and subtracted, and so you would propagate that accordingly down here. So we've done part A, single phase equivalent. Part B, find the line currents. We've done that. Part C is where things can get a little confusing because there's multiple ways to proceed. So what I'm going to do, what I've decided to do for this first problem, is to actually show you both ways. None of the math is complicated. It's just a slightly different way of thinking about it. They're both equivalent, and ultimately, half of you would probably do it the first way, and the other half of you would probably do it the second way. So rather than have confusion, I'd really rather show you how to do it both ways, and then you can just do what you want, knowing full well that everything is consistent. So I'll label them method 1, method 2. What are we trying to do? Find the phase voltages at the load. So you need to know that that means phase voltage means voltage across this load, which is VAB, and then voltage across this, which is VBC, and then voltage across this. So AB, BC, and CA. Of course, it's going to be the same song and dance as before. Let's try to find the voltage for the A phase, AB, V capital AB. Once we find AB, we just use the phase sequence minus plus 120 to find the other two. There's actually two different ways to find AB, and let's talk about them to compare and contrast them both, and then we'll do them both on the next board. All right, what are the different ways to do it? All right, now that I've calculated AA, I know the line current, so I know AA, okay? That means I know this line current, and I have an equation that we've developed and used a lot in the last few sections in a delta load to convert between a line to a phase current. It's a square root of 3 times, this guy would equal square root of 3 times the IAB times a phase shift, right? Which is going to be adding or subtracting 30 degrees depending on that guy. So you know that you can shift between this current and this current by that equation, right? Once you have this current, then it's just Ohm's law, right? The voltage across this is equal to IZ. So that's easy, right? You shift to get IAB, then you multiply by this to get VAB. That's what we said we're trying to find. The phase voltage at the load means VAB. Once you have that, you add, subtract 120 to get the other two. That's method number 1. That's what we're going to do first. But you know what? I think it's actually going to be clearer if I just go ahead and do method number 1 and then talk about method 2, because method 2 I have to talk a little more about. It's I think actually cleaner and clearer to do method 1, but I do want to show you method 2 because you'll see why in a second, but it's useful. It's very useful. So the first step here is let's shift from AA to get IAB, the current flowing through there. And to do that, let me call this method 1. Okay, so what I'm going to do is I'm going to say this equation, AA is equal to the square root of 3 times the phase current, AB, capital AB, and it's going to be a phase shift of minus or plus 30 degrees. Remember, for the current shifting in the delta load, it's minus plus. We choose, for positive phase sequence, what's on the top, negative phase sequence on the bottom. This problem is a positive phase sequence, so we're just going to use the negative sign, which is on the top. I know what this is, so I'm going to stick it in here, and I'm going to solve for this current. All right, what is AA? It is 2.4 angle 36.87. So 2.4 angle 36, I should say negative 36.87. That's this line current. Equals root 3 IAB capital, angle negative 30 degrees. All right, so to find the current AB, capital AB, I'm going to take this guy, 2.4 angle negative 36.87. I'm going to divide by the square root of 3, and I'm going to divide by this, which is going to be dividing by negative 30 degrees. Now you can just stick it in your calculator like that, but in a lot of books you'll see it written as 1 over the square root of 3 times this phasor, 2.4, at an angle of negative 36.87. And then when you take it and move this upstairs to make it multiplication, it changes it to a positive 30. So now you can add these guys together and multiply this times the magnitude, essentially, is what you're doing. And what you will get is IAB. Capital A, capital B. Let's see, let's double check here. 2.4, negative 36.87 plus 30. Okay, what you get is 1.39 at an angle negative 6.87 degrees amps. I'm going to go ahead and circle this. Actually, I'm not going to circle this because that's not what we're asked to find, but it's an important first step. So what we found is we found this current through this load here. Okay, but the question wasn't find the current, for part C anyway, it's find the phase voltage at the load. Now that we know what this current is, how do we find the voltage, VAB, which is the voltage across the load? The voltage is going to be the current times the impedance, but here's the tricky part. You got to keep straight what you're doing. You are mixing a little bit here, because originally you said, well, it's hard to deal with delta load, so we'll just convert it to an equivalent Y, and then we will come over here and we will use that in our single phase equivalent circuit. But honestly, once you've used it for the purpose of finding the line currents, you're kind of done with the equivalent single phase equivalent circuit, and then you have to go back to dealing with the real load you have. That's why we use this and shift it using the delta load shift formula to get the real current flowing in this leg, right? And then when we want to find this voltage, we say this current times this impedance, the actual real impedance from the circuit that you've built, not the equivalent impedance for the Y load, because ultimately we only use that equivalent impedance just to find the line currents. That's the only reason we did it. After that, we're basically using everything as it's really in the actual circuit that we've built. So current times impedance. V is equal to IR, right? Or IZ. Okay, so what we do is we say VAB is equal to I times Z. I is this guy, 1.39 angle negative 6.87 times the impedance. What impedance do I use? It's the real impedance in the real triangle, and we go back to our problem for that. It feeds a delta load, 118.5, J 85.8. That's the number we stick in here. So it's 118.5 plus J 85.8. That's what we stick in there. So VAB is equal to, let me just double check my signs here, 202.72 angle 29.04 degrees, volts. That's VAB. Now that is 1/3 of the answer because we have to find all three of them, but now we know the voltage across this, which is exactly what we were asked to find. Again, method 1, first of all, it says find the phase voltages at the load. Method 1 says, okay, I use the equivalent single phase circuit to be able to find the line current. I have an equation to shift from line current to phase current, which is what I did down here on the next board. Once I have this, I multiply this times the actual impedance in my problem because that current's flowing through that impedance. in order to get the voltage across it, which is the phase voltage at the load for phase A. So that's what I did. Once you have AB, you can get the other two just by adding and subtracting. We're going to do that in a second. But before we add and subtract 120, which I know that you know is very easy to do, let me go and explain, and we'll perform method number 2 to find VAB so that you understand what's going on there. Once I prove to you that the equivalent way of finding VAB works, then we'll just add and subtract the 120 at the end to get the other phases here. Okay, I almost didn't even want to show you this, but I think it's actually really important for you to understand. So here we go. How do you do method number 2? Okay, method 2 is a little weird because what I told you is take this delta load, calculate an equivalent impedance, which would be a Y load if we were to build a Y load there, and use that equivalent impedance in the single phase circuit. And then I said, you know what, this equivalent impedance doesn't really exist. We didn't really build it, but we could if we wanted to, and it would be modeled the same way from here backwards. It would look the same to everything else in the circuit. And then I said, hey, this neutral terminal, I want you to label it, even though it doesn't really exist in our problem, because it would exist if we really did build the single phase equivalent using the equivalent Y load. If we actually built that one instead, then this neutral terminal on the load side would be real. But here's how we do method number 2. What we're trying to find is VAB, which is the line-to-line current. How would we do that if this were the other types of problems we did a long time ago? Remember, we did like 8 or 9 YY problems. Not Y delta, YY. A long time ago, we already introduced that. We worked those ad nauseum. How would you find VAB? VAB, B's not even on the single phase equivalent, but you know it's down here in the other phase somewhere. How would you do it? Well, you would say, well, I know the line current, so let me find VAN, the voltage across this load. Pretend for a second it's not a delta circuit, pretend it's really a Y circuit, and this is what was here. You would find the voltage VAN, and then what would you do? You would use a voltage shift. If for the YY circuit, remember the phase voltage and the line voltage are different for Y circuits. And so we have an equivalent shifting formula to switch between, just like we have one for the currents here in the delta case. We have one that we've used many times already to shift between the voltages when they're different in the case of the YY circuit. So if this were a Y circuit, and I just told you, hey, find VAB, you would say no problem. I would multiply, I would get the voltage drop here, that would be VAN, and then I would use the voltage shift going from phase voltage or line to neutral voltage to line voltage. And we know what that is, we've used it before, and that would be VAB. Now, it may not be obvious to you, but it turns out that doing that for this equivalent single-phase circuit, even though we don't actually have this circuit built, gives you the exact same value for VAB as we got doing it the totally other way. It's because this delta load can be modeled as an equivalent Y load, even though it's not really there, even though there's really no neutral terminal there, even though you may not even say, this makes no sense, VAN isn't even real. It's not real, because it's not even there. That's okay. Mathematically, it still works out because it would be there if we really built it the other way, the equivalent way. So let's do that. Let's find VAN. We're going to do that by multiplication, by this current times this guy, this impedance, VAN, then let's shift it. Let's see what we get. I've already given you the punchline, so you know what we're going to get, but let's go ahead and do it anyway. So let's go here, and then we'll say method 2. And it's really powerful for you to know this because different problems are going to be easier to solve different ways. So method number 2, VAN, which is the line to neutral at the load side, is going to be equal to the current, the line current times the impedance. The impedance there was 39.5 plus J 28.6. Okay. Now the line current, IAA, where's it at here? The line current is right here, 2.4 negative 36.87. So let's do it here. 2.4, I got to make it a phasor. We'll do it like this. Negative 36.87 times this impedance, 39.5 plus J 28.6. Notice the impedance I'm using here is the impedance in my single phase equivalent circuit. I'm trying to find VAN. So it's this current times this impedance, which we know it's not really real, but it could be if we built it that way. It's equivalent to our problem, so we're going to find VAN right here. VAN is going to be, when we do that multiplication, 117 20.04 and an angle of negative 0.96 volts. Now the weird thing is there really is no VAN for our actual problem. Our actual problem has a triangle here and there is no neutral, so there is no VAN. But it turns out to be a useful mathematical tool because, you know, I don't know how far you are, how far into it into your math studies there are, but there are all kinds of equivalencies we can do. You know, we can go into the Fourier transform domain and solve a problem in the Fourier transform domain that's not really particularly real either, but it's a little easier to deal with mathematically there, and then you can transform back and get the answer. Or we've done it with Thevenin equivalence, where I can take a giant network and I can condense it down to a small little network of equivalent parts that behave just like the big one, and it makes it easier calculationally. Well, the same thing here. This is something that doesn't really exist in our actual circuit because there's no neutral terminal, but we're kind of in another domain of equivalency where this particular concept can help us find our answer because we could have built a circuit a different way. We just didn't in real life. We're modeling it as something different. So we have VAN there. Now how does that help us find VAB? We have a voltage shift formula, V capital AB for the YY case, which is equal to, let's see here, it's equal to square root of 3 times VAN, the line to neutral, and it's plus or minus 30. Remember, we've been doing minus plus because we've been dealing with these delta circuits, but if you go back to the notes for the YY circuits for the voltage shift, it was plus minus. And since it's a positive phase sequence, we choose the first sign here, okay? So now we have VAN, we just stick it in here, do the multiplication, we get VAB. So what we get is, yeah, let's do it here. Square root of 3 times VAN 117.04, angle negative 0.96, and then we have this plus 30 here. And that's a positive number. Let me just check, make sure I'm caught up here. And what did we get for VAB? When you stick that in your calculator, you get 202.72, angle 29.04. So this is exactly what we got right here, 202.72, 29.04 for the angle. I think that's pretty cool. Cool enough that I wanted to show you that that's totally possible to do it that way. So you actually have total freedom when you do these problems. When you have an equivalent single-phase circuit, mostly we use it just to find the line current. But if you find VAN, you can use a voltage shift as if it were a YY circuit and still get VAB, a line-to-line voltage, in exactly the same way that we did it for method 1, which was a little more straightforward, I think. Particularly method 1's a little more straightforward to me, but they're both totally equivalent ways to do it. All right, and you might get some decimal differences somewhere in the angles, so it just depends on what you carry through your calculation, but these are both equivalent ways to doing it. So we found the A phase part of that. So in order to find BC, which is the B phase voltage, it's going to be the same thing, 202.72 at an angle of 29.04. That's what we got. And then if you go back here to find the B phase, you subtract 120 degrees. All right? So then what you will get is VBC is going to be equal to 202.72 angle negative 96. So I'm going to circle that because that's the B phase. And for the C phase, VCA is 202.72, 29.04, and you add the 120. So VCA 202.72 angle 149.04. Okay, so we've circled, I guess we've circled both of those. So now we have completed the third part of this problem because now we have VAB, that's the phase voltage across this part of the triangle. And then we have VBC and VCA. BC is this one, CA is that one. So now we've completed most of the problem right here. Okay. So we've done the single phase equivalent, we found the line currents, and we found the phase voltages at the load, and we actually did that 2 different ways. Now, part D, find the phase currents at the load. What is a phase current? It's the current going through a phase, so IAB. But then we remember, wait a minute, we actually solved for IAB as part of some of this other stuff. We had to calculate IAB right here. We had to calculate that when we did method 1 to find the voltage drop across that part of the load. So we actually already have what IAB is, right? And we can just rewrite it again, and we'll just do the adding and subtracting accordingly. So let's switch to this, I guess. So the next part of this guy is IAB was 1.39. That's the current through phase A of the load, negative 687 degrees amps. Okay, and then IBC is going to be the same thing, 39, negative 687. But then what do? You subtract 120 degrees. IBC is equal to this, 1.39, and you have an angle right here of negative 126.87. That's the B part of the phase current for the B part. And then for the C part, CA, 6.87, negative 6.87, and I add 120. So that means CA is 1.39 at an angle. When we add these guys together, we get 113. Whoops, let's make this clear. 113.13 amps. I'm trying to save space here so that I can get the last part of the problem in without erasing anything. Okay, so that was part C, and fortunately we didn't have to do anything else for part C because we had already found the phase current. Now, let me just go ahead and say really quickly, we already found IAB, the phase current for phase A, only because we did method 1 first. We found the current through the phase, and then we found the voltage across the phase. That was method 1. If we had tackled it method 2, then we wouldn't have found that current as part of that solution, and we would have had to kind of do it from, we would have to do this calculation again. But since we already found it as part of method 1, we're basically done. Okay, there's one last part. It says find the line voltages at the source terminal. So this part, you got to think back to some of the previous stuff we've done. It's at the source terminal. So this is the source here. So we have little a. So we're dealing on this side of the circuit. It's the line voltages. So instead of capitals, it's going to be lowercase, and it's going to be AB. That's a line to line. When we say line voltages, it's line to line voltages. So not VAN, that was a line to neutral voltage, VAB. How do we find VAB? This is where we go back to some of the stuff we've done in the past for a YY circuits. How do we do it? Well, it's very similar to how we did method 2 over here. We know what this source is. We know what this current is. So we know what the voltage drop across this part of the source winding is. So we have everything we need to find what VAN actually is. That's a line to neutral voltage. And in a Y source, like all the problems we've done in the past, the line voltage and the phase voltage is different. And we convert with the square root of 3 rule for voltages, just like we did from method 2 over there. So our strategy is going to be figure out what VAN is, and then just shift it with the square root of 3 rule to get VAB. That's what we've done for the YY circuits all along. And then we'll just find the other ones by adding and subtracting 120. So what is VAN anyway? Well, you can either see it or do it with KVL, but basically you could write a KVL loop which walks around this, back around here, and solve for VAN. If you were to do that, this is a voltage rise, so it'd be, notice the current is going this way. So this is a voltage rise, we treat that as negative, and then this would be a voltage drop, we treat that as a positive drop, and then this would be another voltage drop, we treat it as a positive drop. So let's go ahead and do that rather than skip steps. Let's go ahead and show everything the way we would do it. What we would have is, when we're doing a KVL walk, we would walk through the source, which is a voltage rise, so it's treated as a negative. Then the voltage drop from the internal impedance of the source is the current times the impedance, 0.2 plus J, 0.5. And then we have a voltage drop, VAN, and that's equal to 0. So everything, I want to make sure you understand that equation. we're just doing a KVL loop. We're literally walking from this neutral terminal up through all of this stuff to the A terminal and then straight back down to here. That's a total loop there because we want to find VAN. So we start here. This is a negative 120. And then this is a positive because it's a drop. The voltage drop will be the current times the impedance. And then this will be another positive VAN. Make sure you understand that that's exactly what we wrote down. A negative because the source is walking uphill, then a voltage drop through the winding impedance, then a drop through VAN. Why are we doing that? Because we want to find what VAN is. Now, some of you guys can just look at it and write the equation for VAN explicitly, but let's move this junk to the other side. It'll be 120, positive 120, 0, minus IAA 0.2 plus J 0.5. And now that I've got it in a form where I can substitute very easily, I'll just go ahead and substitute 120, angle 0, minus, what is IAA? That's the line current. 2.4, negative 36.87. Negative 36.87. 0.2 plus J 0.5. Let me catch up and make sure I've done this correctly. So 120 minus 2.4, negative 36.87 times that. Yeah, so take this in your calculator, multiply it, take this, subtract whatever that comes out to be, and the VAN, the voltage between the line and the neutral there is going to be 118.90 at a negative angle of negative 0.32 degrees volts. Now this isn't what we wanted, that's VAN. This is the voltage between the line and the neutral of the source of the generator. But it actually asks us to find the line voltages, which means line to line voltage, VAB. And we have a voltage shift formula for that, which we will write down to refresh your memory. We just used it, actually, for method 2 a second ago. But the basic idea is the line to line voltage, VAB, is equal to the square root of 3 times the phase voltage, VAN, and you have a phase shift, plus or minus 30 for voltages. For voltage phase shift in a YY circuit, it's plus or minus. We know it's a positive phase sequence, so we choose the positive sign right there. So all we do is stick VAN in here. So we say square root of 3, square root of 3 times this guy, which is 118.90 at an angle negative 0.32. And we have a phase shift of 30 degrees. Okay? So you just multiply the magnitudes, add 30 degrees to that angle, and what you get is VAB, which is a line-to-line voltage at the source. That's exactly what it asks us to do, which will be 205.94. at an angle of 29.68. And that's voltage. And I'm going to circle this one because it's one of the 3 answers that we need. And then the rest of this problem is cake, because now that we have the A phase line-to-line voltage, we just find the B phase, which will be BC, is the same thing. 205.94, angle 29.68. Now we have the A phase. To get the B phase, we subtract 120 degrees. Okay, so we get BC is 205.94 at an angle of negative 90.32 degrees. Negative 90.32 degrees, that's BC. And then we have the last guy, VCA, lowercase c, lowercase a. We start over with the A phase, 205.94, angle 29.68, and instead of subtracting, we add 120. So the last thing we need to write on this problem, which was already too long, 205.94, angle. We add these guys together and we get 149.68 volts. All right, I told you that was going to be a long problem. But we need to do a real problem. Now you see why I spent so much time on explaining that shifting formula for the voltage for the YY circuit. And then we spent a lot of time on shifting formula for the current in the delta circuit. And then we spent some time telling you how to convert the delta to an equivalent Y and how to draw the single phase equivalent. And then we did some practice using that formula. Because when you put it all together, if I would have just started this set of lessons on delta loads as like, here's a problem, then most people would be lost. I mean, even I would be lost because you don't have any practice with any of it at first. But now we put all the pieces together and we do it as follows. Part A, draw a single phase equivalent circuit. Literally everything was given in the problem statement except for the load. So when you have a delta load, if you want to do a single phase equivalent, you must convert to an equivalent Y. This is the impedance you put in your single phase equivalent. Okay, part A, done. Part B, find the line current. Use your single phase equivalent. Voltage divided by total impedance gives you this line current. Right? Then, once you have it, it's a balanced three-phase set, so the B phase is subtracting 120, the C phase is adding 120. Part B, done. Part C was the longest. Find the phase voltage at the load. Phase voltage at the load is the voltage here. I want this one, I want this one, and I want this one. So let's focus on the A first. So here is my strategy. We know this. Use the current shift to find this current. Then we know the voltage by V is equal to I times Z. So let's look at how we did that. First, we started with the line voltage we had, the line current we had. We shifted to find the phase current in the delta load. We found IAB, and we used that to multiply by the real impedance of the delta given by the problem statement to give us the voltage across that leg. Right? So that was correct. This was one of the three answers. But then we said, hey, there's another way to do it. You can actually go back to your single phase equivalent, even though you didn't build any of this stuff, and you say, well, I can calculate what VAN is as if it were a Y load, by current times this impedance that gives us VAN. Then I can use the voltage shift formula to find VAB, capital AB. Okay? So we found VAN by multiplying current times that impedance in the single phase equivalent to find VAN. Then we shifted by using the voltage shift. Remember, it's line-to-line voltage, square root of 3, phase voltage, and it was a plus minus. We chose the plus because of the phase sequence. We did the multiplication and we found VAB and we saw that they agreed exactly, so you have multiple ways of solving these problems. Once you have the A phase, you subtract 120 to get the B phase, you add 120 to get the C phase. Boom, part C, done. Part D, find the phase currents at the load. We realize as part of doing this problem that we actually already calculated one of the phase currents, so we just started with that as a starting point. Right here, and we subtract 120 to get this and add 120 to get the C phase. Boom, we're done with part D. Right here. Part E, find the line voltages at the source. You got to say, what is a line voltage? It's not this, it's not AN, it's AB, BC, CA, at the source, right? So to get it, we just say, well, we know the current going through this. We'll find VAN. Once we know it, we'll use the voltage shift for Y sources or Y circuits to get the other deal. So we wrote a little Kirchhoff voltage loop to figure out what AN was. Sometimes you can just see this from the circuit. We calculate it using the source minus the voltage drop of the impedance there in the source winding. We find VAN, that was given by this. And then we just use the voltage shift to go from line to neutral to line to line. Again, it's positive 30 because it's positive phase sequence. We put everything in there. AB is what we get for an answer. That's a line-to-line voltage at the source, and then we subtract 120 and add 120 to get the other phases. What a monster problem. I mean, none of it is like three-dimensional calculus or something crazy, but it's enough to make your head feel like mush when you're done, just because there's so many different ways to make a mistake. So we had to build ourselves up to it. Finally, we finished a real problem. We're going to do a couple of additional real problems to give you more practice, but honestly, if you understand this, and hopefully I've done a good enough job so you do understand this, then you really can tackle all of these problems because they're all the same way. They're all the same thing. You do a single phase equivalent, you find the line current, and then depending on what they ask, you're going to have to do various things. So I've tried to give you enough of a guideline here so you can kind of get some comfort for yourself, but you must do this problem yourself. You have to, even though you've just seen it. If you just say, oh, I get it, and go on, you're going to bomb something because you will not do well with this stuff until you sit down and solve it yourself. So do that, and then follow me on to the next lesson. We'll get some more practice with Y delta three-phase circuits.